Okay, guys, this is the final frontier of further maths for you with me. I'm going to teach you differential equations from Core Pure. Then I'll teach you the next chapter, which is modelling with differential equations, which is such a common topic. I think it came up in 3 exam questions across two exam papers last year. Differential equations is just mega topic. And then we will do differential equations in FP1 as well. So actually, I think you're going to really enjoy this topic. It's very interesting. It follows on from everything that we've been doing in regular maths as well. Nahid and Mehek, I think you may not have seen like a bit about differential equations in regular maths. So I'm going to do a couple of examples that are like it from regular maths, and then we're going to push on to the stuff that's from normal maths. And then when it comes back in regular maths, you're going to be like, this is so easy, okay? So it says here, differential equations are equations which relate x and y with derivatives. For example, the rate of temperature loss is proportional to the current temperature. So here you've got dt is equal to minus kt. Can we just try and break that down? What does dt actually mean?
The derivative of t with respect to t.
The derivative of t with respect to t, but what does that mean in context?
The rate of t.
The rate of change of the temperature is what it means. This means the rate of change of temperature, and the k means is proportional to the current temperature is t that we've got here. So this is talking about the current temperature, whereas dt is talking about the rate of change of temperature. Why is it minus? Because it's cooling down, it's temperature loss, okay? We've got other ones that we've come across before. So here we've got the rate of population change is proportional to p brackets 1 minus p over m, where p is the current population and m is the limiting size of the population. This is the Verhulst-Pearl model. So it's a particular thing that connects together what the rate of change of the population is to current situations of population. Another one that we've got here, suppose that X is the gross domestic product. The rate of change of GDP is proportional to the current GDP, which implies that if a country has got a high GDP, what would you predict about that country if they've got a high GDP? Pardon? The growth rate of GDP will also be high. In other words, rich countries, we expect to get richer. Poor countries will be getting richer, but at a slower rate, okay? And most things in real life that we try and study are connecting things that are changing to other things that are changing. And actually, it's quite easy to set up these things and say, oh, well, I think the population is going to be related to the current population in this way. But then to try and find out what an equation is for the population, to go back to the original equation, is a bit difficult. So it says here, as you might imagine, they're used a lot in physics and engineering, including modelling radioactive decay, mixing fluids, cooling materials and bodies falling under gravity against resistance. A first-order differential equation means the equation contains the first derivative, dy by dx, or dp dt, dt dt, but not the second derivative or beyond. And what we will be looking at to begin with is first derivatives. We will then look at second derivatives as well, but we won't go any higher than second derivatives, okay? So a quick recap of some of the things that is from regular maths, which is a particular technique that you will have hopefully remembered called separating the variables. So here, if you have that dy by dx is a function in x multiplied by a function in y, you can use this technique. And it says that x and y are said to be separated because we can express the right-hand side as a product of 2 separate expressions, one in terms of just x and one in terms of just y. So we already know how to solve some differential equations by using separating the variables. The way we do this is we would divide both sides by g of y, the function of y. Then you would multiply this dx by to the other side, and then you just integrate both sides. So you get the integral of 1 over g over y with respect to y is equal to the integral of f of x with respect to x. So we're going to find the general solutions. General solutions means that there's going to be some kind of plus c, because there's many different solutions that would work for this, to dy by dx over y minus x. Now what we should notice to begin with is the right-hand side is a product of 2 x and y functions. So that means we can use separating the variables. Spoiler, we're not going to be doing this in the future. We're going to be doing ones where you cannot separate the variables here. So I'm going to divide both sides by y, so I get 1 over y dy by dx is equal to minus 1 over x. Then I'm going to multiply up the dx like this. So we have all the y terms on the left, all the x terms on the right, and they integrate. 1 over y dy is ln y. This integrates to minus ln x plus c
No,
plus ln k. You could do plus c, but ln k will just mean if everything is in terms of ln, it's way easier to combine all of these things together. So we then get ln y equals ln of k over x. So we can just say y equals k over x. Okay? Now, if we were going to think about what this looks like as a graph, well, it's like, could be this, it could be this, it could be terribly drawn here, but it's any of these kind of graphs that you've got. And if k were a negative number, then it could be this graph, this graph, this graph. So all of those solutions would satisfy this differential equation for a general solution. What would we need to do if there was a particular solution? What would we need to be told in the question?
Substitute values of y and x.
They'd need to give you some values of y and x. They might say, solve this equation given that when x equals this, y equals this. And then you could do that to find out what k is. Okay? Nothing new, unless you're Nahid and Mehek, because I know you haven't done this in your class, but there's nothing super different from this.
And Luke.
Pardon?
And Luke.
And Luke, but I think Luke has looked at the videos for this. Have you? Yeah? So we're now going to use the reverse product rule, because this is now proper further math stuff, okay? It says, we will see in a bit how to solve equations in the form dy by dx plus py equals q, where p and q are functions of x, okay? In this case here, p and q are not constants, but they are functions of x. And it says we'll practice a particular part of this method before going for the full thing, okay? So it says here, find the general solutions of the equation x cubed dy dx plus 3x squared y equals sine x. Now, first of all, what is different about this equation to the ones that we just had on the previous page?
You have trigs and x and y together.
We've got trig and stuff, yeah, but there's another difference that means we can't do something on the previous page. Pardon? There's a product of x and y, but it's being added to something. So no matter what you try and do here, you're unable to separate the variables. Okay, you're unable to separate the variables by having all the y variables over here dy and all the x variables over here dx. So you cannot do this, right? There's a big clue in the title. But do we think what we might be able to rewrite this left-hand side as? What does the left-hand side look like it could be?
Oh, that thingy. We can take out x cubed.
So I'm going to ask you to refer back to what the title says.
What's the product rule again?
What's the product rule again? Is this a joke?
Because you know that there's a y in both terms, right?
Yeah.
And y, the derivative of y is dy dx.
So the derivative of y is dy by dx.
And the derivative of the other one is the 3x squared.
Okay, so what is this whole thing the derivative of?
After you do product rule, so it's post-product rule.
So it's the post-product rule of what?
So initially it's x cubed y.
X cubed y.
Oh, that's clever.
Now let's just explore this a bit
They're
more, okay?
derivatives of each other.
If I was going to differentiate this with respect to x, first of all, I would keep this the same and differentiate this with respect to x. Then I would keep this the same and differentiate this with respect to x.
Product rule.
You just take the highest powers and put them together.
We just not writing out U and B.
So, yeah.
Yeah, I need to remember how like that works.
Okay, do you see what's happened? So here, this purple equation was the original one. I can rewrite the left-hand side as this. Okay? So if I can rewrite the left-hand side as that, what can I do to try and solve the differential equation?
Yeah.
Walk away, huh?
I want to try and solve this differential equation. What do you think I can do? Come on.
Take dx to the other side.
Take dx to the other side.
And the x squared.
No?
Why not?
Then integrate the right side.
And then integrate the right-hand side.
You get
So why is the d? Where does the d
cos
go?
it.
The d, it's not dy, it's just like,
This.
I'm saying I've differentiated this with respect to x. If I want to undo,
That be on the top.
if I want to undo differentiating with respect to x, I integrate with respect to x. What I'm actually doing here is I'm integrating this side with respect to x, and I'm integrating this side with respect to x. If we know that the derivative of this thing, when you integrate it with respect to x, is this. Okay, so that's why we're not actually multiplying by dx. So we get x cubed y equals minus cos x plus c.
Yep.
Now, that means y equals minus cos x over x cubed plus c over x cubed.
So we can remove that. So very,
Sorry?
this is general. Because can we just remove the x cubed?
No, because we want a general solution. No, because this is, you can't replace this with, I don't know, say k, where k equals c over x cubed. You cannot do this because it's got the variable in it.
Oh.
You can only replace one constant with, you could have said, if it was a different question, where k equals 3c over 17, you could replace that because it's just a constant with a constant. This is replacing a constant with a variable? No, because this variable here is fundamentally changing what the graph might look like, okay? It's going to have an extra over x cubed feature in the graph.
So C minus cos x over x cubed.
So you have to introduce the constant here, and if you do any manipulation, you have to manipulate the constant. Because if you're not manipulating the constant, you're leaving off a part of the variable that is fundamental to what that looks like, okay? So we dived in pretty deep with that bit to begin with, but let's just quickly do some differentiation of some of these things that I've got here. So I'm going to differentiate these using the product rule. Ruhan, can you do this first one, just differentiating this using the product rule?
X squared dy by dx
Plus 2xy. Luke, can you differentiate this using the product rule?
Yeah, sin x dy dx plus cos xy.
Maybe I actually probably would prefer to write that as y cos x. So it appears whatever term ends up in front of the dy by dx will be on the front of the y in the integral. Look here, sine x, and then this was y, sine x, y. X squared, y. Also, that's the derivative of that. Sorry, that's the derivative of that. This differentiates to this differentiates to this, and this differentiates to this. That's the product rule there. So if we're going to now try and go backwards, what do we think this is the derivative of?
X to the power 4y.
X to the power of 4y. This is the derivative of e to the power of xy. And this
Ln xy.
is the derivative of,
Ln x and 1 over x.
no, it's just the derivative of, I don't know if you said it the first time and I just didn't hear you. What's this?
I don't want to say it again just in case I'm wrong.
Luke, what's this derivative of?
Don't want to do that.
That one.
Nahid?
Yeah.
Y ln x.
Or that way, yeah. That's the Ln x one.
Probably.
Because when you differentiate that with the product, you keep that, differentiate that, there it is. Keep that, differentiate that, there it is. Okay? So this is a very, very, very quick differential equation to solve, but it requires you recognizing it. Okay? Now, there's a technique we're going to learn that will work for these equations later, but it adds in another 5 or 6 steps, probably 4 or 5 steps rather than 5 or 6. And if you want to do 4 or 5 steps extra in an exam where you're pushed for time, then be my guest, but I don't think you're going to want to do it. So you want to try and spot these things quickly, okay? Can I go on to the next page?
Yes.
Mehek, you should be writing this as we're going, okay?
You're doing it so fast, so I'm trying to listen instead of like.
Okay, fine. So we've actually already done this one, okay? If you wrote it out on the previous page, then that's fine. But I'm just going to do it as a quick reminder, a quick recap of what we just said. I have already done this question just now, but we'll do it once more. Why not? So we said that this was the derivative of x cubed y, which was sine x. And then what did we do next?
Then we fundamentally
Yeah,
and
so that was
then
fine.
integrate it.
Yeah, and technically what we're actually doing here is I'm integrating this with respect to x. And I know when I integrate this with respect to x, I get this. Because when I differentiate this with respect to x, I get this. So I'm integrating this side, and I'm integrating this side. And we got x cubed y equals minus cos x plus c. You must make sure you've got the plus c. So y equals minus cos x over x cubed plus c over x cubed. And that thing has to be written as c over x cubed because it fundamentally is contributing a 1 over or something over x cubed to the function. Okay? Got it?
Yeah.
So we're going to do a couple more.
1 over x.
So, what does the left-hand side look like the derivatives of?
Y over x.
It looks like it is the derivative of y over x. You must check this to see that it works. So you would have, well, you'll have 1 over x dy dx from differentiating the y. When you differentiate the x part, you would get, when you differentiate 1 over x, you get minus 1 over x squared, and then you have the y there as well. So that is equal to e to the x. So we get y over x equals the integral of e to the x. What am I saying? Plus c. Stupid me. Of the integral of e to the x dx. So y over x equals e to the x plus c. So y equals x e to the x plus cx.
We don't want to factorize it here.
No, I'm happy with it like that, personally. But you can factorize it if you want. How could you check that this answer was correct?
Integrate. I mean, no.
Differentiate.
Differentiate it, and then,
It should rearrange to that.
yeah, differentiate it and substitute it back into that thing that we've got there. Should we just do it really quickly and see it works? Okay, so dy by dx is equal to, what does x e to the x differentiate to?
X e to no e to the x plus e to the xx
Plus x e to the x plus c. Okay, so if I substitute in, I will have 1 over x multiplied by e to the x plus x e to the x plus c. That's 1 over x multiplied by dy by dx minus 1 over x squared multiplied by x e to the x plus c x. And we hope that this is going to simplify and give us e to the x. So when we multiply the brackets, you get e to the x over x plus e to the x plus c over x, just expanding that, minus, what does this expand to?
e to the x over x
Good.
Plus c
c
over
over
x.
x
Minus,
c over x.
minus c over x. That cancels,
We have to
equals e to the x that we wanted. Okay, so you can check these. And when I was your age and did these in the exams, I would just check them. It's just like if you were solving an equation, like 3x plus 1 equals 7, and you go like x equals 2, you can substitute it in and check that it works. So why wouldn't you do the same thing here if you have a spare moment? Probably not going to have a spare moment, but you can check it, okay?
Well, that sort of one stuff, I can just do that in my head. I can sub in x
Wow.
equals to 2.
Yeah, but we're not doing that in our exams. This one you'd have to do longer.
That, yeah, but that would waste time.
That's the point.
Would it waste time? It just depends. Like if it was one that you weren't sure about, like when I did my uni exam, I had some time and I just checked it all. I put it all back in and I was like, I 100% have got that correct.
It's so small. You do a uni exam and still have time.
So what do we think this left-hand side is?
2xy squared.
2xy squared.
Yeah.
Yeah.
That was very
Not
quick.
2xy squared.
Yeah, it is. Because that side differentiates to there, and then There's 2x.
Yeah.
Because it's 2y that's left. That it divides 2.
So that's a lot harder to see that one, that it's 2xy squared. Because
Too quick for my brain.
the y squared will differentiate to a 2y dy dx. So you've got a 2y dy dx. So it would have been a 2x that you would have had in there. So that reveals the fact that it's a y squared in the function. So you get d dx 2x y squared equals x squared. So we get, what was that? Do you want me to go over that again?
Yes.
Okay, so here, we know that it's going to feature a y squared in the bit that we're doing the derivative of. When you differentiate y squared with respect to x, what do we get?
2y divided x.
2y, but because it's implicit, you get dy dx. So when you differentiate the y squared part over here, you would get 2y dy dx, and it looks like the leftover part that we've got here is a 2x to give us this bit, which means this part here must be a 2x when you do the product rule. And the derivative of the 2x is 2, and we keep the y squared that was there. You're just going to need to spend a bit of time by thinking about how do I go backwards with the product rule. So then we get 2xy squared equals the integral of x squared dx. So you get 2xy squared equals a third x cubed plus c. Let's just get me a bit more space. Divide everything by 2x if we want to. So y squared equals a third, a sixth, thank you.
X squared plus c.
A sixth x squared, not plus c, plus c over 2x. Now if you wanted to, you could change this bit. What do you think I could suggest you could change this bit to?
1 over 2x plus c.
No,
Not times c.
that's not going to do anything different though.
2x
No, you could replace it with just k
Okay,
over x,
because the over 2.
where k equals c over 2. Because the over 2, just in case they were telling you, show the general solution is this, and you got this, they're the same thing as each other because you could replace k with c over 2. You're allowed to replace this like this. You wouldn't be allowed to replace it in any other kind of way. So we get y equals, and I don't know if this is any better, but I quite like it with y squared as the subject. So you've got 3 questions to do in exercise 7A. Let's go.